Imagine a star. Not our sun, but a star far more massive. A star that lived a brilliant but short life, burning through its fuel with ferocious intensity. When such a star dies, it doesn't just fade away. It goes out in a blaze of glory. A supernova explosion that can outshine its entire galaxy. If the star is massive enough, its core collapses under its own immense gravity. Protons and electrons are crushed together, forced to become neutrons. What remains is a sphere barely the size of a city like Mumbai, but containing more mass than our own sun. This is a neutron star. A single teaspoon of neutron star material would weigh about 6 billion tons. That's the weight of every single human on Earth, compressed into a volume smaller than a sugar cube. They also spin incredibly fast. Some rotate hundreds of times per second, faster than a kitchen blender, creating powerful magnetic fields that are trillions of times stronger than our planets. Picture two of these cosmic behemoths, each weighing more than our sun, but compressed into a sphere just 20 kilometers across. They are orbiting each other in a deadly silent waltz. According to Albert Einstein's theory of general relativity, these massive, accelerating objects are constantly churning the very fabric of spacetime around them. They are creating ripples in spacetime itself. As they radiate gravitational waves, the two neutron stars lose orbital energy. This causes them to draw closer. Their dance speeds up. In the final moments, they are whipping around each other thousands of times per second. They are moving at a significant fraction of the speed of light. As they get closer, the immense gravity of each star begins to deform the other. They are stretched and distorted into teardrop shapes. Tidal disruption. In the last millisecond before they merge, the space between them has vanished. They are now touching. The dance is over. The cataclysm is about to begin. The moment of contact is instantaneous and catastrophic. After being stretched by immense tidal forces, the two city-sized stars collide. Each packs more mass than our sun, slamming together at a third of the speed of light. The impact unleashes a powerful burst of gravitational waves, ripples in spacetime itself. The merged remnant is a chaotic maelstrom. For a fleeting moment, it forms a hypermassive neutron star, spinning hundreds of times per second. This rotation generates a powerful centrifugal force, temporarily staving off total collapse. But this state is profoundly unstable and cannot last, as it rapidly sheds energy. The hypermassive star collapses in on itself with breathtaking speed. In less than a second, the core is crushed beyond the limits of matter, forming a black hole. An event horizon, the point of no return, expands outwards, swallowing the star's heart. A new singularity, a point of infinite density, is born. But not all matter is lost. A swirling superheated accretion disk of debris forms around the new black hole. Its rapid spin and intense magnetic fields act as a cosmic engine, launching two powerful jets from its poles. These are relativistic jets, accelerating particles to over 99.9% the speed of light. As these jets tear through the surrounding cloud of ejected material, they create powerful shock waves. The shocks unleash a focused burst of high-energy light, a short gamma-ray burst. For a few spectacular seconds, this burst can outshine all the hundreds of billions of stars in its host galaxy combined. The sheer scale of this energy release is difficult to comprehend. In just seconds, the event unleashes the energy of hundreds of millions of our sun's entire lifetimes. It's more energy than all the stars in the Milky Way will produce in a year, concentrated into one fleeting, violent cosmic flash. A significant amount, perhaps several times the mass of Jupiter, is violently ejected in all directions. This cloud of debris expands at incredible speeds, about 10 to 30% of the speed of light. As it flies outward, radioactive decay creates a different kind of explosion, one that glows for days and weeks. This is the kilonova, a glowing, expanding sphere shifting from blue to red over days. Inside the fiery, expanding cloud, neutrons are rapidly captured by nuclei in the R process, rapid neutron capture. This builds the heaviest elements. From Earth, a kilonova looks like a star suddenly appearing where none existed. Initially, it's incredibly hot and blue, shining for a day or two before fading. The first confirmed kilonova, GW 170817 in 2017, was a watershed moment. For the first time we saw light from a collision first detected via gravitational waves. We watched cosmic alchemy in real time. Still, for days a single kilonova can be as bright as a billion suns. For decades, we've pondered a fundamental question. Where do the heaviest elements in the universe come from? Gold, platinum, uranium, other heavy elements. There was a missing piece to the puzzle. The neutron-star merger is that place. The universe's ultimate element factory. The R process, rapid neutron capture, is the key. An iron nucleus might rapidly absorb neutrons, ballooning in mass. It climbs the periodic table to become silver, iodine, gold, platinum, uranium. One merger can make gold equal to several times the mass of Earth. Let that sink in. One 10-minute event, millions of light years away, created more gold than exists on our planet. When you hold a piece of gold in your hand, you are holding stardust, matter forged in the death dance of two neutron stars collided long ago, perhaps before our solar system was born. We are, in a very real sense, the children of neutron star collisions. We are not just living in the universe is living in us. In 2015, humanity gained a new sense. Using observatories like LIGO, we could finally hear the universe. For the first time, we directly detected gravitational waves, the subtle ripples in space-time predicted by Einstein a century earlier. This achievement confirmed a cornerstone of general relativity and opened an entirely new window onto the cosmos. When two incredibly dense objects like neutron stars spiral towards each other, they violently churn space-time. As they draw closer, their orbital speed increases, causing the frequency and amplitude of the gravitational waves to rise. This creates a signature sound we call a chirp, a signal that starts low and builds to a crescendo at the moment of merger. On August 17, 2017, this cosmic symphony peaked. The LIGO and Virgo detectors registered a powerful chirp from colliding neutron stars. Just 1.7 seconds later, NASA's Fermi telescope detected a gamma-ray burst from the same patch of sky. For the first time, we had both heard and seen the same cosmic event unfold as observatories worldwide turned to watch. This was the dawn of multi-messenger astronomy. The gravitational waves gave us the inside story, the masses of the stars, and the raw physics of the collision. The light, from gamma rays to optical waves, told us about the spectacular aftermath. We saw powerful jets blasting out, and in the glowing debris, found the chemical signature of heavy elements like gold and platinum being forged, solving a long-standing cosmic mystery. It's like a cosmic thunderstorm. The gravitational waves are the thunder, the deep shockwave revealing the event's raw power. The light is the lightning, the brilliant flash illuminating the aftermath. Separately they are informative, but together they provide a complete three-dimensional picture of the storm. This combined approach is revolutionizing our understanding of the universe's most extreme phenomena, unlocking secrets previously invisible to us. Gazing up at the night sky, it's easy to think of cosmic cataclysms like neutron star collisions as distant, abstract events, happening light years away and eons ago. But this couldn't be further from the truth. In a very real sense, the story of these violent stellar mergers is our story, a history written in the very atoms that constitute our world. The very elements that make our world valuable, technologically advanced, and even biologically complex were forged in the heart of these 10-minute cosmic infernos. The gold in our electronics, the platinum in our medical devices, the uranium that powers our cities, and even the iodine essential for life itself, all were synthesized in these moments of extreme physics. Without them, our world would be unrecognizably different and perhaps lifeless. It's a cosmic recycling program on the grandest scale. Stars live and die, creating lighter elements like carbon and oxygen. Some of the most massive stars collapse into neutron stars. When two of these city-sized, super-dense objects collide, they unleash a kilonova, creating the heaviest elements and flinging them across the galaxy. This precious debris seeds the interstellar clouds from which new stars and planets will form. The calcium in our bones was made in a star, the iron in our blood in a supernova. But the gold on our finger was born in a kilonova. Every heavy atom on our planet and within our bodies is a relic, a direct beneficiary of this ancient, violent, and beautiful cycle of cosmic creation and renewal. This understanding should fill us with a sense of wonder and humility. The forces that created the precious materials of our world are almost beyond comprehension. It reveals our intimate connection to the cosmos, showing that we are not separate from the universe, but a living, breathing part of it. It reminds us that the universe is vast, powerful, and full of processes that dwarf our everyday experience. We are stardust, yes, but we are also the children of kilonovae. It's a powerful testament that even the most violent and seemingly destructive events in the cosmos can be the ultimate source of creation, scattering the seeds of future worlds across the darkness. We are living in a golden age of astronomy. The discovery of neutron star mergers has opened a new chapter through gravitational waves and through light. What was once theoretical is now observable. As our detectors become more sensitive, we expect to see these events not just once every few years, perhaps once every week, or even once every day. We are looking towards space with plans for missions like LISA, which will be able to detect gravitational waves from different kinds of cosmic events. Each new detection will provide another piece of the puzzle. We might even find something completely unexpected. The universe always has a way of surprising us. We will build a complete catalog of these cosmic collisions, mapping out the history of heavy element creation throughout the universe. The universe is full of wonders, and as we continue to look and listen, we will continue to find them. The frontier is endless.